Okay, today in this video, we are going to solve few numericals from physics of semiconductor devices, where we will see few numericals based on density of states and the Fermi Dirac distribution functions. So let us do the questions. Okay, so the first question we took is calculate the density of states per unit volume with energies between 0 and 1 electron volt. So we need to find out the density of states per unit volume. So as we know the density of states, okay, we define density of states as what? The number of electronic states present per unit volume per unit energy range. Now the energy range is given to you 0 to 1 electron volt. So simply you write the density of states value and then integrate it from this range 0 to 1 electron volt. So if we'll do this, we can write, so the density of states per unit volume, I can write integration from 0 to 1 electron volt, that's the energy range, and then the density of states value. Okay, and then we'll integrate it. Okay, so just substitute the value that we determined in one of the videos I have done. So you can refer to that density of states, what is the value that we determined. So 2m to the power 3 by 2 divided by h cube. H is Planck's constant here. Integration, I took the constant terms outside, okay, and then the function of E will be inside. So D, so this is what we got. Now if you will write it again, 4 pi 2m to the power 3 by 2 h cube as it is we wrote, and then this integration gives you what? 2 by 3 e to the power 3 by 2, right? The limit here is 0 to 1 electron volt. Okay, so this is for like okay, so this function, right? Then you substitute the value like 4 pi. Okay, here if I write 2, m is our 9.11 into 10 to the minus 31 kg mass of the electron. Okay, this to the power 3 by 2. Okay, and then substitute the value of h as 6.625 into 10 to the power minus 34 joule second. So this cube, and then you have 2 by 3 1 electron volt. I substituted e to the power 3 by 2, this is 0, so just substitute 1 electron volt. 1 electron volt is 1.6 into 10 to the power minus 19. Okay, substitute that and then 3 by 2. If you will calculate this, this will give you 4.5 times 10 to the power 27 per meter cube. Okay, or else we can just say, if you want to write in centimeter cube per centimeter cube, then also you can write it as 4.5 into 10 to the power what? Here you got 21, right? Okay, this states per centimeter cube. Okay, so centimeter cube. So these many electronic states will be there. 4.5 into 10 to the power 21 electronic states will be there in this range of 0 to 1 electron volt. Okay, per unit volume. So this is what we can calculate. Fine. So let us now move to the second question. The second question says calculate the temperature at which there is 1% probability that a state 0.30 electron volt below the Fermi energy level will not contain an electron. You need to revisit to for the theory part. I have discussed in one of the videos what is Fermi Dirac distribution function and how it gives you the probability of finding the electron in a particular energy state or electron state, right? So now here if you can see, the question says calculate the temperature here. So we need to find out this temperature at which there is 1% probability that a state 0.30 below the Fermi energy level. So the energy gap is given 0.30 electron volt below the Fermi energy level will not contain an electron. So Fe actually Fermi Dirac distribution function gives you the probability of finding the electron in a state, and not finding the electron means you need to find out actually 1 minus Fe, right? So 1 minus Fe is actually the thing which will give you actually not finding the electron. So let us do the solution for this. So simply, as I said, 1 minus f of e. F of e is Fermi Dirac distribution function. For more clarity or understanding, you can revisit the video that I have made on Fermi Dirac distribution function. Okay, so 1 minus, this is the function, 1 plus exponential e to the power. Okay, this is e minus ef, the gap, divided by kT, Boltzmann constant. T is the absolute temperature. So we need to find out T. So make T as the subject and solve it. So here it is given 1% probability of not finding. So 1 minus Fe is given 1%, which is 0.01. I can write that 1 minus 1 divided by 1 plus exponential e to the power. E minus Ef is given 0.03. This is the gap given. E minus Ef, you substitute that 0.30 divided by kT. Okay, substitute it, and then you solve it for kT, right? So solving it for kT, I'm just writing it directly. You can just calculate it. 0.06529 electron volt. Okay, use a calculator and make kT as subject. Okay, and then you calculate it. Okay, then from that you can find out T by just dividing the K value, which is a known constant. So 0.06529 electron volt divided by this K value is 8.62 into 10 to the power minus 5. Substitute, this gives you actually 756 Kelvin if you calculate. Okay, so K value I substituted. K is the Boltzmann constant given by 8.62 into 10 to the power minus 5 electron volt per Kelvin. Okay, so this is the value we substituted and we got this. So now what do you mean by this? 300 Kelvin is your room temperature, right? 756 Kelvin, if you'll see, and you are finding that what temperature there is 1% probability that a state this below the Fermi energy level by this amount 0.30 electron volt will not contain an electron. You can determine this way. Okay, so let us move to another question. Okay, so the next question says, calculate the energy in terms of kT. Okay, K is Boltzmann constant, T is the absolute temperature, and EF, the Fermi energy level. Okay, at which the difference, okay, the difference between the Boltzmann approximation, okay, and the Fermi Dirac distribution function, Fermi Dirac function, okay, is 5%, okay, of the Fermi function, the Fermi function. Okay, so what we need to do? Calculate the energy. We need to calculate the energy in terms of kT and EF. So we will write energy in terms of kT and EF, Fermi energy level, at which the difference between the Boltzmann approximation and the Fermi Dirac function. Difference between these two is 5% of the Fermi function. So we'll need to just a simple mathematical equation we need to write. So the inequality, the function is actually given here. The equation is given here. So what we need to write is the difference between the Boltzmann approximation and Fermi Dirac distribution function. So let us write the Boltzmann approximation and the Fermi Dirac distribution. For this also you can refer to that video of Fermi Dirac distribution function that I have discussed. There also I have discussed what is Boltzmann approximation and what is Fermi Dirac function in detail. So you can refer to that. So we can write the Boltzmann approximation, which is actually exponential e to the power minus of E minus EF divided by KT, okay, divided by KT. This is your Boltzmann approximation minus the Fermi Dirac distribution is given by 1 plus e to the power, okay, E minus EF divided by KT, okay. So this must be equal to what? 5% of the Fermi function. 5% means 0.05, we will write 0.05 of the Fermi function, which is 1 divided by 1 plus e to the power E minus EF by KT. So this is the equation, and you solve it and then find out. Okay, so here in this is little bit lengthy. I'm just trying to do it. So what we're going to do is multiply both the sides with okay, let me just write it. Multiply both sides by 1 plus exponential of e minus ef by kt. So you know what is the objective behind this. So if I'll multiply this, we can further simplify one side actually. Okay, so that it can be further simplified. So I'm just clearing it. So what I will get if I'll multiply this factor both the sides. So I will write exponential of the Boltzmann function was e minus ef divided by kt. Okay, and then I will multiply this with what 1 plus exponential of 1 plus exponential e to the power, okay, I mean e to the power e minus ef divided by kt. Okay, so this is what I multiplied, and then minus, it was like 1 by 1 plus exponential of e minus ef by kt multiplied with this. Okay, so that will be 1 only. Okay, 1. This is the objective, that's why we just multiplied, and the right hand side will be only 0.05. Okay, just to simplify it further, we multiplied both the sides with 1 plus exponential of e minus ef by kt. So that can further be simplified as exponential of whatever the term here over here. Okay, after multiplication you can just write it as e minus ef divided by kt. This is what we got after multiplication, right? So this is equal to 0.05. Okay, so that we can write 1 divided by, this is minus of this, so 1 by, take the reciprocal, 1 by e minus ef divided by kt. Okay, this will be 0.05. Okay, so we can further write it as exponential of e minus ef divided by kt will be 1 by 0.05. Okay, because I just do the reciprocal of both the sides, so that I can write e minus ef here can be written as kt times logarithm of ln of 1 by 0.05. Okay, so if we'll calculate this, okay, this ln 1 by 1.05 around 3, so you can write this to be 3 times kt. This is okay. So our objective is to write energy in terms of Fermi energy level and kt. So what we got, e is equal to ef, the Fermi level, plus kt, right? So this is what we got. So what we need to write is calculate the energy in terms of kt and ef, at which the difference between Boltzmann approximation and the Fermi Dirac function is 5% of the Fermi function. So we got this, e is equal to ef plus kt. So that will be our answer. Yeah. Okay, let us move to the next question. So one more question. So it says determine the probability that an energy level 4 times kT, K is Boltzmann constant, T is absolute temperature, above the Fermi energy is occupied by an electron at T equals 300 Kelvin. Okay, so what do we say? T equals to 300 Kelvin. Practically think of it, T equals to 300 Kelvin is your room temperature, right? So we need to find out, determine the probability. We are going to find out the probability, okay, that an energy level 4 kT, 4 times kT above the Fermi energy level is occupied by an electron at T equals to 300 Kelvin. So we are going to find out the probability, right? So determine the probability whether an electronic state at a height of 4 kT above the Fermi energy level is occupied at room temperature or not. So probability means we need to find out the Fermi distribution function, because that gives us the probability of finding the electron in a particular electronic state, right? So in the solution we can just write what is Fe. We know the value f is equal to 1 divided by 1 plus exponential e to the power. Okay, this is e to the power, we write this way, e minus ef divided by kt. Okay, so we can write this to be 1 plus exponential of e minus ef. The gap is already given, which is 4kt here, right? So substitute that, so we can write it to be 4kt divided by kt. Okay, so here, so you can see, you cancel kt and then you write whatever the value, 1 divided by 1 plus, now you got e to the power 4, which gives us 54.6. use your calculator to calculate this. So you got 1 divided by, this is 55.6, that gives you 0.1798. By using calculator it will calculate, which is nearly equal to your 1 point, if you'll multiply with 100 it gives you, sorry, 18%. Okay, around 18%, so we can write that. Okay, so multiplied with 100, so 17.98 you got, so that gives you 18% probability. So the probability that an energy level 4kt above the Fermi energy is occupied by an electron is 18%. So there is 18% chance that the electron is occupied, I mean, an energy level 4kt above the Fermi energy level is occupied by an electron. Okay, so this is how we can do the questions. One more question we can do. So this question says the Fermi energy is 0.25 electron volt below the conduction band. I'm just writing it as CB, conduction band. Okay, the value of NC, effective density of states for the conduction band. Okay, for silicon, for NC and NV, what is NC and NV? You can refer to my previous videos where I have discussed about NC and NV. Okay, just check those out. So NC, when equilibrium distribution of electrons and holes were calculated, there I have shown what is NC or NV. Okay, effective density of states for conduction band, effective density of states for the valence band. Okay, so for silicon at T equals to 300 Kelvin. This is always given as T equals to 300 Kelvin in most of the problems, because this is considered to be the room temperature. Okay, is okay, the value of NC is given as 2.8 into 10 to the power 19 per centimeter cube. So effective density of states in the conduction band is given. Okay, now what you need to do is calculate the probability that a state in the conduction band is occupied by an electron and calculate the thermal equilibrium electron concentration okay, in silicon at T is 300 Kelvin. So you can see it's a direct question. The Fermi energy is 0.25 below the conduction band given, below the conduction band. So this is the energy gap between EC and EF. Right now, this is given EC minus EF. Actually, you can see EC minus EF is known 0.25 electron volt. The value of NC is given, effective density of states over here. Calculate the probability that a state in the conduction band is occupied by an electron. So we need to find out the probability. Okay, probability means what? Fermi Dirac distribution function at E is equal to EC, because it says in the conduction band. So in the conduction band is what? F of E we need to calculate when E is equal to EC. So that is one thing, right? And then calculate the thermal equilibrium electron concentration. We need to find out the value of electron concentration, which is n0, right? So these are the things we need to find out. So we will find out the Fermi Dirac distribution function when E is equal to EC. That is one, we will find out. Okay, simply from the from the formula of Fermi Dirac distribution, and then we need to find out n0. Okay, so I can just write the formulas over here. N0 is actually NC, then e to the power Okay, we have minus EC minus EF, which is given in this question. You can see 0.25 electron volt divided by this kT. Okay, so this is the formula, and f of E is equal to EC. F of E is also a known value, which is 1 divided by 1 plus exponential power e to the power EC minus EF divided by kT. Both the formulas are given, all the data are known, just substitute it. Okay, let me just clear it and I will write it. So F, first thing we need to find out, E is equal to EC. Okay, so I will write this to be 1 plus e to the power EC minus EF divided by kT, right? This is the formula. So which is nearly equal, we can write exponential of minus of EC minus EF divided by kT. Okay, considering the Boltzmann approximation. Okay, so here you can just write then f of EC is equal to exponential e to the power, or else you can substitute over here, it is known, so you can that will also find out, or else you use this approximation. Okay, so exponential minus 0.25 divided by 0.0259, that is the value of kT at room temperature. So that gives you 6.43 into 10 to the power minus 5. Okay, so this is what we got, right? This is the probability of finding the electron in the conduction band. Okay, so here also you can write dc minus ap is, substitute 0.25 electron volt kT and then calculate the whole thing. But yeah, because the Boltzmann approximation holds good here at room temperature, you can just substitute that as well. Okay, then for finding the electron concentration, you can write NC, effective density of states in the conduction band, exponential of minus of EC minus EF divided by kT. Okay, so this is what we can write, and then substitute the value is given. 2.8 into 10 to the power 19 was the value for NC that was given, and then e to the power, this is EC minus EF minus 0.25 electron volt divided by this value kT is 0259 for room temperature 300 Kelvin, and K value, okay, 8.62 into the minus 5. So substitute that and then you can calculate it. It gives you 1.8 into 10 to the power 15. Okay, so these many electrons per centimeter cube. So this is the value you can write. Okay, so these are the few numericals we did based on density of states and your um, Fermi Dirac distribution function. Okay, we will continue with some more numericals from physics of semiconductor devices in some other video. Stay tuned. Thank you for watching.